Hello everyone. In this module 4, you will learn about bagging trees and random forest models. A random forest is one of the most powerful machine learning algorithms for regression and classification tasks. Previously, we learned that tree-based methods are simple and useful for interpretation. However, they have an instability issue and other limitations. So in this module, you will learn about bagging trees and random forest methods for overcoming the limitations of tree-based methods. The bagging trees and random forest methods produce multiple trees combined to yield a single consensus prediction. You will learn how combining a large number of trees can often result in dramatic improvements in prediction accuracy at the expense of some loss in interpretation. Here we go. Let's recap the significant limitations of the tree-based method. First, it can be unstable due to a greedy hierarchical structure. One change at the top split can change the remaining tree. Second, it will be difficult to use trees for making inference due to the stepwise search. Third, trees generally do not have the same level of predictive accuracy as some of the other regression and classification approaches. Lastly, trees can be very non-robust. In other words, a small change in the data can cause a large change in the final estimated tree. However, by aggregating many decision trees using methods like bagging and random forest, the predictive performance of trees can be substantially improved. An ensemble method is an approach that combines many simple building block models in order to obtain a single and potentially compelling model. These simple the building block models are sometimes known as weak learners, since they may lead to mediocre predictions on their own. I will now discuss bagging and random forest models, and these are ensemble methods for which the simple building block is a regression or a classification tree. Because of the instability of trees, they are great candidates for methods like bagging and will reduce the variance. The main idea is to grow a set of number of B trees from a bootstrap sample and average the prediction, where theta hat B are the estimated parameter for feeding trees from the bootstrap sample. The bagging means here bootstrap aggregating, and bagging will help will variance reduction but not bias. So previously in the bias variance trade-off model, we simulated a 5,000 polynomial model with different training data set. You can consider the bagging method is averaging predictive value from these 5,000 polynomial models on the red line here. But here we are using tree-based models instead of these polynomial models. And this figure here on the right side of the slide shows a simple example of bootstrapping. It simply means extracting training data from the original data set to train our models. In this example figure here, we have 5 training data sets, and we will have 5 different tree-based models from these 5 different training data sets. Please also remember that bootstrapping is used in many situations in which it is hard or even impossible to compute the standard deviation of a quality of interest directly. We will see here that the bootstrap can be used in totally different contexts in order to improve statistical learning methods such as decision trees. As I mentioned earlier, the decision trees suffer from high variance. This means that if we split the training data into 2 parts at random and fit a decision tree both halves, the result that we get could be quite different. In contrast, a procedure with low variance will yield a similar result if if it applied repeatedly to distinct data sets. Linear regression tends to have low variance if the ratio of number of data to number of parameter is moderately large. And bootstrap aggregation, bagging, is a general purpose procedure to reducing the variance of a statistical learning method. Here, I'm going to show you how the bagging method can reduce the variance of model. Please pause this video for a moment and check if you can still remember the properties of variance and covariance. Since we will aggregate several map models, we will focus on how the variance can reduce the aggregate by aggregating many different models. So let theta be something we wanted to estimate. For example, estimating an evapotranspiration value using temperature, and theta hat here is estimated evapotranspiration data set. And let's assume we have an m numbers of models to estimate theta, which produce the m number of estimates. One straightforward but general way to make an ensemble prediction is by averaging all the predicted value here. And the expected value of the ensemble and variance are shown below here. Please pause the video and try to understand the variance of ensemble. This equation. And one thing you should notice here is that the variance of ensemble is a function of correlation coefficient, the red box here. This means that if each model is mutually independent, we can reduce the variance of the model tremendously by aggregating these models. So the essential idea in bagging is to average many noise, but approximately unbiased models and hence reduce the variance. Thus, when bagging trees, grow deep trees to reduce bias and use many bootstrap samples to reduce variance. This is the key point. To make a long story short, random forest is a modification of bagging that attempts to build decorrelated trees by considering a restricted set of features for splitting. Let me briefly explain the training and prediction processes of the bagging method. First, we draw a bootstrap sample, G star of size n from the training data set. For example, here we have B number of bootstrap sample, which means we can grow a B number of trees. And second, grow a random forest tree to bootstrap data by recursively repeating the following these steps for each terminal node of the tree until the minimum node size, the m mean, is reached. The three steps are: first, select the number of variables at random from the p variables. Suppose we have 5 predictors to train the model, say temperature, precipitation, soil moisture, humidity, and wind speed. And for this step, we only choose 3 random predictors, say only soil moisture x1, humidity x2, and wind speed x3 to grow a tree. Second, pick the best variable split points among the n variables. And third, split the node into 2 daughter nodes till the minimum node size, the m mean, is reached. The step 2 is just simply repeat step 1 b times an ensemble of each tree's output. The prediction will be based on all these b numbers of trees and average their predicted values. This is quite simple. So there are 3 primary tuning parameters for random forest models. You will need to keep this in mind if you are planning to use the random forest method in your research. Here I only include parameters names for scikit-learn package, but R and MATLAB also have a similar package for creating random forest models. First, M here controls the number of predictors that are evaluated for each split. For example, 3 predictors among 5 predictors. And second, the depth and size of the trees are controlled by setting the minimum number of observations in leaf node or the depths of trees. And third, the number of trees is another tuning parameters, but we want these to be as large as possible. And these are our arguments or parameters for sklearn random forest regressor. As you can see here, your random forest model can be totally different from mine, even if we use the same training data sets, because you can take all these parameters yourself. Furthermore, please note that these tuning parameters can be determined from cross-validation or OOB error, the auto back error value. So what is the OOB error? OOB metric is measuring the accuracy of prediction using R trees in random forest ensemble for which it was omitted during training. Thus, it kind of acts as a semi-testing instance. In specific, auto-back OOB error, also called auto-back estimate, is a method of measuring the prediction error of random forest, bootstrap decision tree, and other machine learning model utilizing bootstrap aggregating method, the bagging method. An OOB error is the mean prediction error on each training sample xi using only the trees that did not have xi in their bootstrap sample. For each observation, xi, yi construct its OOB prediction by averaging only those trees corresponding to bootstrap sample in which observation I did not appear. So let's quickly go to the dim node and see how we can make a random forest model and implement OOB in sklearn package. So here we have the xtrain x test, ytrain y test data from train test split function. And here are parameters that we can tweak. So here I set the 100 of n estimator and 2 for the mean samples leaf, and max feature auto means the random forest regressor will figure out how many features they will use for splitting. And bootstrap and OOB score to be true because I want to calculate the OOB score. So to implement OOB in sklearn, you need to actually specify these. Okay, so please run this code block and follow my lecture video. Let's go back to our slide. So let's check the training accuracy here. A red solid line shows the training accuracy with respect to different number of estimators. As expected, the accuracy of the model when evaluating the training set is very high, the solid line here, red line here. However, this is meaningless, because you can very well be overfitting with your data, and thus your model is rubbish. Please review the bias variance trade-off lecture if you don't understand this part. And next, when you check the auto-back score, the OOB score shown in the blue dashed line here, we can estimate the actual accuracy of our model. This is the accuracy while it's evaluating our instance in the training set using only the trees for which they were omitted. Now let's check the score on the testing set, the green dashed line here. Yeah, here. And we can now see that the accuracy here measured by OOB is very similar to that obtained with the testing data set, the blue dashed and green dashed lines. It does follow through the theories that the OOB accuracy is a better metric by which to evaluate the performance of your model rather than just the score, the test score. This is a consequence of bagging models and cannot be done with other types of methods. Please remember these scores serve as close validation loss as well, and OOB error can be calculated without having test data set. So here we learned that OOB is a very straightforward way to estimate the test error of bagged model without the need to perform cross-validation or the validation set approach. The OOB approach for estimating the test error is particularly convenient when performing bagging on large data set for which cross-validation would be computationally onerous. As we have learned, bagging typically improves accuracy over prediction using a single tree. However, unfortunately, it can be challenging to interpret the resulting model. Recall that one of the advantages of decision trees is the attractive and easily interpreted diagram that results. However, when we bag a large number of trees, it is no longer possible to represent the resulting statistical learning procedure using a single tree, and it is no longer clear which variables are most important to the procedure. Thus, bagging improves prediction accuracy at the expense of interpretability. Although the collection of bagged trees is much more difficult to interpret than a single tree, one can obtain an overall summary of importance of each predictor. For example, we can use variable importance metrics. Let's see how it works. At each split in each tree, the improvement in split criterion is the important measure attributed to the splitting variable and is accumulated over all the trees in the forest separately for each variable. The importance of predictor J in a single tree, the large T, can be calculated from this equation. And that is the importance of feature J in tree T's in the total gain from R splitting involving feature J. In this equation, the sum is over R split T in trees large T. The importance of predictor J in the forest is then the average importance of all trees in the forest here. We can easily calculate the importance of predictors using the scikit-learn package. Let's see how we can do it. Here, the feature importance here will give you how much each predictor contributes to growing trees. So this plot shows an example of what predictors are most important in determining baseball players' annual salary. For example, if a player has more runs batted during his career, the CRBI predictor here is he is very likely to have a higher salary than someone who only hit but did not run a lot, the C hits predictor here. Yes, I really hope you will have a chance to implement this powerful method, the random forest method, when you build a model for your research. This is the last slide for module 4.